So in this video we want to develop the solution process that we use when the characteristic polynomial has complex roots. So if we have complex roots, what we want to remember is that complex roots show up in conjugate pairs. So if we have a root 1, and it's customary to do a plus bi for complex numbers, but we're already using a and b for our second order linear homogeneous differential equation. So instead of using a and b, maybe we can use alpha and beta so that we don't get the a's and b's here confused with the a's and the b's that we see right here. And the solutions always occur in conjugate pairs. So if you get alpha plus beta I, you also get alpha minus beta I as a solution. So for the differential equation, when the roots are complex, we really do get two solutions. It just happens to be that our solutions have a complex component to them. We get a solution y sub 1 that looks like e to the alpha plus beta I times x, replacing the root with the alpha plus beta I. And we get a second solution y sub 2 that looks like e to the alpha minus beta I, alpha minus beta I times x. And then what we want to recognize is that this can be broken into pieces. The e to the sum of two things can be rewritten as e to the alpha times x times e to the beta I times x, because when we have the same base and we take the product of those bases, we add the exponent. So here this can be broken into e to the alpha x times e to the opposite of beta times x. And then the tool that we're going to use to what we want to do is try to manipulate things so that we wind up with a set of solutions for our differential equations that don't involve the complex unit. And the tool that we're going to use to do that is Euler's formula. So this is a famous formula, e to the I theta equals cosine theta plus I sine theta. And using Euler's formula, we can take and rewrite the e to the beta I x term. So we would still have the e to the alpha x, but this would be times e to the beta I x can be rewritten as the cosine of the coefficient on I, which is beta, so cosine beta plus then I times the sine of the coefficient on I, which in this case is just beta, so I sine beta. And this will equal e to the, we still will have the alpha x, and then it will be e to the, so we have e to the negative bx, so it's going to be the cosine of the coefficient on, I will dropped my I there, it's net minus beta I x. So here we're going to get the coefficient on the I is the opposite of beta. And then we're going to get plus I times the sine of the opposite of beta. And then what we want to remember is the cosine function is an even function, so the cosine of the opposite of beta is the same as the cosine of beta, so we can substitute beta in for opposite of beta. And the sine function has odd symmetry, so the sine of the opposite of beta is the same as the opposite of the sine of beta from our trig identities. And so once I get it into this form, I can think about how to construct additional solutions. So we need to remember two things from homework 1, where we developed the preliminary theory we needed to work with second order differential equations. And the first thing that we learned was that if we have solutions y1 and y2, then the sum of any two solutions is also a solution. It just creates a third solution, y sub 3. we learned that if y sub 1 is a solution, then any multiple of y sub 1 is also a solution. So we're able to do linear combinations of our solutions to get additional or new solutions. So here I have y sub 1 and y sub 2 as solutions, and they can be written in this form. So what I want to recognize is that I can construct a third solution, y sub 3, by taking the sum of the first two solutions I have. And the sum of the two solutions will still be a solution. So if I take y sub 1 plus y sub 2 and I add these two together, the e to the alpha x will factor all the way out. And I'll be left with cosine beta plus cosine beta is 2 times the cosine of beta. And the plus I sine beta will cancel with the minus I sine beta. So I'll get this as a solution. So the sum of any two solutions is a solution, but the scalar multiple of any solution is also a solution. So if I take a half of this, I'll still have a solution. So e to the alpha theta times the cosine of beta is still just a solution. And of course, any scalar multiple of this is a solution. So any y equal to e to the alpha x cosine beta will be a solution, any scalar multiple of that. So y will do c sub 1 e to the alpha x cosine beta. Any scalar multiple of this, by our preliminary theory, is going to be a solution as well. And then I can do the same thing again. I can create a fourth solution by taking the difference between these two solutions. So if I do y sub 1 minus y sub 2, well, the e to the alpha x will factor all the way out. And I'd get cosine beta minus cosine beta is 0. I'd get plus I sine beta minus I sine beta would be times, it's going to be 2 i's times the sine of beta. And any scalar multiple of y, so any multiple of y sub 4 is also a solution. So I can multiply this by negative 1/2 I. So times negative 1/2 I. And I times I is I squared is negative 1. So we get negative 2 times negative 1/2 is 1. So that tells me that e to the alpha x times sine beta is a solution. So I can create another solution, let's call this y sub 5 and y sub 6, by taking c sub 2, any scalar multiple of this. So c sub 2 times e to the alpha x sine beta will be a solution. So then it's fairly straightforward to demonstrate that the Wronskian of each of these will not be equal to 0, so that e to the alpha x cosine beta times e to the alpha x sine beta are linearly independent. To do that formula, we just calculate the Wronskian. I think it's visually evident that these aren't going to cancel out, but we could calculate the Wronskian just to be sure that these form a linearly independent set of solutions. And if we have a linearly independent set of solutions, and we have two linearly independent solutions for a differential equation, then we can create a general solution for our differential equation by taking the sum of those two solutions. So c sub 1 e to the alpha x times the cosine of beta plus c sub 2 e to the alpha x times the sine of beta. And of course e to the alpha x is showing up in each of the two terms, so we can rewrite this in probably what's the more typical form, e to the alpha x times c sub 1 cosine beta plus c sub 2 sine beta as the general solution for the second order linear homogeneous solution that has constant coefficients. So again, the alpha and the beta are coming from the real and the imaginary components of the roots r sub 1 and r sub 2.